this lecture, I shall start with the chapter 1 of our textbook, Topology by James Munkres. James R. Munkres. Okay. Before getting into the set theory, let us first understand a few logical symbols that we use to write the set theoretical arguments. The first one is this symbol that denotes and, this denotes or, and there's this symbol. We use it to write three statements. We can use it for anything. One is for all, or the next one is for every, or you can also use it for each. Okay. The next one is this, that is there exists. Okay. And then if I write it this way, I mean there exists no such element, or the statement like that. Okay. And if I write it like this, then this means there exists a unique element, or whatever. The statement goes like this. Okay. After this, we have this symbol, or we sometimes also use a vertical line, that denotes such that. Okay. And this denotes negation of the statement. So in my previous lecture, I told you I used the bar notation for negation. This is nothing but this is equivalent to negation of P. Okay. Both the notations are the same. Just from here onwards, I shall use this notation as per the textbook. Okay. The next one is this, that is, this is implication. Okay. We pronounce it as implies. Okay. And if I write it the other way, this is implied by. So if I have two statements, let's say P and Q, if I write like this means P implies Q. And if I write the other way, this means P is implied by Q. And if I write it like this, then this means implies and implied by. In this case, I can write, we can also write it as if and only if, because you know that this is if P then Q statement. So this is if Q then P. So in both, if I club these two, then I can write P if and only if Q. Okay. And the next one is this symbol. It's called turnstile. This means this proves. This proves. So I told you that these two statements, that is P implies Q and not Q implies not P, are logically equivalent, and hence I also told you that it is sufficient to prove not Q implies not P if we have to prove Q. So just to see where to use this symbol, I'll show you. We can say that not Q implies not P. This proves P implies Q. Okay. these are a few notations that we use in this chapter or anywhere after this. So it's very important to remember these because I'll be using these very frequently. Okay. So now let us start with the first chapter, that is set theory and logic. Okay. So I shall approach the chapter in a very formal way, in a very theoretical way. Okay. So I'll use definitions, I'll use theorems, I'll use lemmas to proceed with the chapter. The first one is the very basic definition, that is a set. So what is a set? We all know it is a well defined collection of objects. Collection of objects. So it's very important to be clear about the notations that we use here. So in order to denote a set, we use uppercase letters to denote sets, and to denote the objects of the sets, we use lowercase letters. Okay. So this to denotes objects, or we also call the objects of a set as members. The set members of the set. Okay. And in set theory, if I use the sign equals, this means that those two in this equals, let us treat this in terms of objects. When I say that two objects A and B are equal, I mean that those two objects are the same. It can be a letter, it can be a number, it can be anything. Okay, those two are the same. But when I say two sets are equal, let's say two sets A and B are equal, there are two parameters. One is in terms of the objects, and the other one is in terms of the length. Length is nothing but the number of objects. So I say that two sets are equal only when it has got the same number of objects and all the objects are the same. Okay, so I can say that it has got precisely the same elements. Okay, this is how we can define the equal sets. Okay, after this, as I didn't mention the symbol earlier. If I say that A is a member of A, then I can denote it like this, that is A is in A, or we can pronounce it as A belongs to A. And if A is not in A, I can simply write it this. Okay, this is one thing that we need to remember. Okay, so let us now go to the next definition, that is subset of a set. Okay, we call A is a subset of B. We call A is a subset of B if every member every member of A is in. Okay, so this is what is a subset called, and we denote this as A is a subset of B. Okay, this symbol is called as the inclusion symbol. Okay, so there are two types of inclusions. One is this and the other one is this. Okay, we can also write this as like this. Okay, so this is called just inclusion, and this is proper inclusion. Proper inclusion. Okay, when two sets are properly different, then we use this. Okay, if A is a subset of B, and if A is entirely different from B, then we use the proper inclusion. Okay, this is one. And the next definition is union of two sets. Okay, the let A and B be two sets, and if A and B are two sets, their union is represented as this. That is A. We pronounce this as A union B. So how do we write it? We write it as A union B is nothing but is the set of all x such that x is in A or x is in B. Right? X is in A or x is in B. In English, this or statement is very ambiguous because or can mean that it can be either in A or in B, or it can be in both. That is one possibility. And the other possibility is it can be in A or in B, but not in both. But in mathematics, conventionally, we use x is in A or in B or in both. So if I use or, it means that it can either be in A or in B, or it can be in both the sets. Okay. This is the next one. The next definition is intersection. So similarly, let A and B be two sets, and the intersection of A and B is denoted by this. So, and we define A intersection B as a set of all x such that x is in A and x is in B. This has no ambiguity because x has to be in both A and B. Okay, so there's no ambiguity in defining this type. So when I say that A intersection B, that means it is the common region between the sets A and B. Okay, suppose that there is no common region, I can then I denote this A intersection B as phi. This is where the concept of the set with no elements comes. Okay, so A has got some elements, B has got some elements, but there are no elements in common. So what we can say is the intersection of those two is a set which has got no elements. This set is what is known as null set. Okay, and you can see that from the previous two examples, it's obvious to note these 2 points. A union phi is A, and A intersection phi is phi. Okay, you can verify these two. These are very obvious from the definitions itself. Okay, and now I have a question whether can I say phi is a subset of A? Can I say this? So here we have to look at the definition very carefully, the definition of subset. The subset says that if x is in phi, then x is in A. Right? This is the statement. So yesterday in the last lecture, I told you that see, this P implies Q has got this meaning. If P is true, then Q must be true. Okay. If P is false, then Q can either be true or it can be false. Okay. This is in terms of mathematics, but when you use in terms of like in English, if P is false, then Q must be false. But in maths, if P is false, then Q can either be true or it can be false. Okay, so we can see here. See, rather than analyzing this statement as it is, I'll write it like this. If P is false, then what happens? If X is not in Q, sorry, phi, then it can be true, X can be in A, or there's also one possibility, then X is not in A, right? These are the two possibilities. So you can see that in both the cases we don't have any problem. Still the definition of subset is satisfied because X is not in phi, but still X is in A. That means we can still write phi as subset of A, because if there is no element in phi, if X is not in phi, X can still be in A. There is no violation of the definition. And if X is not in phi, X is not in A. Even here there is no violation of the definition. So with these two, I can write phi is a subset of A. It's very vacuously true. Okay, but the problem comes when X is not in phi. Sorry, the problem comes when X is in phi and X is not in A. And only at this point, this statement, that is phi is a subset of A, is false, right? So we are not getting this statement anywhere in this argument. So we can say that phi is a subset of A without any ambiguity. So this is what I wanted to discuss for today. Thank you for listening. In the next lecture, I shall be going in deep into these statements, that is if and then statements, and we'll see what is the contrapositive, what is converse, what is negation of these statements.